Okay, we were discussing some of the examples. So just I will again go to the same example. So in the previous example, it is just shown that yes, this is the example we were seeing now. So here again by applying the DC dynamic braking, so we have got this particular IF. And again, what is asked in the example is, so this particular example we have seen. So in this case, whatever the particular, calculate the braking current and torque as a ratio of their full load values for 950 RPM. So here we have calculated a particular parameters. Again, we have calculated the JDP positive sequence impedance. Then IP we have calculated. Then IR-P we have calculated. Again, TP we have calculated corresponding. So in the similar way, we have calculated Zn negative sequence just by taking the slip 2 minus S here, 2 minus S. Then we have calculated that IN, IR-N, and then we have calculated TN. So just calculating these all, we have to calculate now the particular net torque T. So then motor current will be again IP plus IN. So it is 45.83. Then full load motor current can be calculated. IF is equal to 442 by root 3 and the square root 0.5 plus 0.4 by 0.05 square plus 2.4 square. So now full load torque will be 3 into this IF square full load current into 0.4 divided by 0.05 slip. Then divided by 104.72, it is omega ms. So just by calculating IF and TF, so we have that particular T and I. So then go for I divided by IF. This is the ratio of that particular current to the full load current, and T divided by TF. So these are the two parameters what has asked. So now we will move towards one more example, 6.7 you can say. So this particular example. So this example is purely based on the transient analysis. So you need to again calculate, you need to understand the transient analysis. So just to see this example, it is a 2200 volt 50 hertz 3-phase 6-pole Y connected squirrel cage induction motor. It has following parameters. So RS is 0.075 ohm, RR dash 0.12 ohm, XS is equal to XR dash 0.5 ohm, and the combined inertia of motor and load is 100 kg meter square. So it is combined. Now calculate time taken and energy dissipated in the motor during the starting. Second, calculate time taken and energy dissipated in the motor when it is stopped by plugging. Now again we have to calculate two parameters. One is time taken and second energy dissipated. So during starting and again when it is stopped by plugging. The third point is there. So third point is asked, what is the resistance? What resistance should be inserted in the rotor to stop motor by plugging in the minimum time? So again, what resistance should be inserted in the motor by plugging to stop motor by plugging? Also calculate stopping time and energy dissipated in the motor during braking. So these three parameters are asked. So in order to calculate first parameter, that is again time during starting and again energy dissipated. So these are the formulas. So the TS, whatever the TS is there, so it is time during starting. So this is the formula for TS, that is 2m under root 1 divided by 4 Sm plus 1.5 Sm, and that is equal to S. Here we need to calculate 2m and we need to calculate Sm. Now again go for Sm. So it is Sm is equal to the formula RR dash divided by under square root RS square plus XR dash plus XS square, and hence you have to put the values here RR dash RS square XR plus XS So now omega ms is 4 pi f divided by p, then omega ms we can get as 104.7. So after getting this, we have to go for T max. Why we are calculating T max? Because we need to calculate Ts. In this case, 2m is there. So in order to have that 2m, we need to calculate omega ms and T max. So T max 3 divided by 2 omega ms into this particular. So just by putting the values, all the values you have to put, and you can get the T max. Now by calculating T max, you can calculate 2m j omega ms divided by T max. So these particular formulas you can get here from this particular whatever the transient analysis. I just show you the transient analysis. Whatever transient analysis of the transient operating conditions is there. So again, it is by taking this particular formula J. So we have this starting and plugging. So all these formulas can get here. So again, it is 2m is there, 2m formula is there here. This is the 2m formula, and you can have this Ts also. So Ts formula, and you can have that particular TB, again time during braking, and so on. So here we have calculated Tmax, and hence we can calculate this particular 2m. So once you calculate 2m, you can go for the Ts. So here you can put the values of 2m and Sm, you can get a Ts, time during starting. This is 1.1077 second. Now energy dissipated in the motor during starting, it is given by Es is equal to 1 by 2 j omega ms square under root 1 plus Rs divided by Rr dash. So just by putting the values, we can get energy dissipated during starting. Second point, time required to stop by plugging. So now time required to stop by plugging, directly use the formula TB is equal to, by putting all these particular formulas, we can get TB is equal to 3.08 second. Then energy dissipated in the machine during braking operation. Again, the second point we need to get EB, that is energy dissipated during braking. This is the formula. So just by putting the values, you can get EB. So in the third point, what is asked, what are the resistance is asked. So what is the resistance to be inserted in that particular motor? So here, as explained in the section 6.7.1, the stopping time has a minimum value of 1.027 2m. So this is the particular, we can say, formula. So just by taking that particular formula 1.027 2m, so now I can write TV as stopping, again time during braking, it is 1.027 2m. So now this particular value is 0.5 second. Now again from equation 6.54, if external resistance is Re, the external resistance is Re, so then whatever the, again here, let us move to that 6.54, it is the 6.54. Now see, the stopping time is again a function of Sm. Stopping time is again a function of Sm. It is maximum slip. It has a minimum value of 1.027 2m at Sm is equal to 1.47. At Sm is equal to 1.47. So corresponding value of rotor resistance is, so this is the corresponding value of a rotor resistance at Sm is equal to 1.47. So this is the, again here he has taken this particular. Now Ri dash plus Re is equal to 1.47 xs plus xi dash, because we are adding an external resistance here, please remember. So it is Ri dash plus Re. So now Re can be calculated so easily just by putting these values, 1.47 minus 0.12. Again it is 1.47 is there. Let us, we are assuming this. So now it is Re is 1.350, or energy dissipated in the motor and external resistance remains same as in 2, that is in case of braking we can say, that is 2673 kilowatt second. So energy dissipated we have calculated in the second point, that is 2673 kilowatt second. Energy dissipated in the external resistor is again external resistor, it is 3 by 2 j omega ms square Re divided by Re plus Ri dash. So now it is just by putting the value of Re and Ri dash, so you will get 1510.67 kilowatt second in the external resistor. So now hence energy dissipated in the motor during braking is 2673, it is second case, minus 1510.67 is energy dissipated in the external resistance. So now it is during braking, energy dissipated will be 1162.33 kilowatt second. So this is how we can solve the examples based on the particular energy dissipation and the time. So this example is asked in the previous question papers. Now we will see some more examples based on speed control of the induction motor. So in this we have seen many speed control techniques. So these are the many speed control techniques. In this case, the very important is stator voltage control, that is variable frequency, variable voltage control. So let's solve one more example on the particular speed control. So here we can see the particular example 6.8. So in this case, a 2.8 kilowatt 400 volt 50 hertz 4 pole 1370 rpm delta connected squirrel cage induction motor has following parameters referred to the stator: RS2 RR-5, XS is equal to XR-5 and XM 80 ohm. Motor speed is controlled by stator voltage control. Here stator voltage control is employed. When driving a fan load, it runs at rated speed at rated voltage. Calculate motor terminal voltage. Motor terminal voltage B is asked. Then current I and torque T at 1200 rpm, and motor speed, current and torque for terminal voltage of 300 volt. There are two parameters. So in order to calculate motor terminal voltage, current and torque at 1200 rpm, so we need to take the again considerations of that particular stator voltage control. So stator voltage control means we can control the speed of that particular motor by varying the stator voltage, because we are having that V square term. If you see the value, whatever the torque of the motor is there, so it is again depending on the particular voltage value, and hence it is depending on the current value. So just by varying the voltage, we can vary the speed of the motor. So in this case, at 1200 rpm, what is asked is, so motor terminal voltage V is asked, and second the particular current and torque will be asked. So here let us see, this is the torque equation. This is the torque equation. So now yes, so we need to again calculate particular torque here. Now this is the formula 3 divided by omega ms v square Ri dash by S and so on. So just in order to calculate that particular torque, we need to calculate particular again S value, and hence the synchronous speed. Now this is the synchronous speed 120 F divided by P. So this is 50 pi radian per second. Then yes, it is again ns minus n divided by 1500, that is ns, it is 0.0867. Put the values. So at full load, so here it is 48.13 Newton meter. Now, for a fan load torque is proportional to speed. We know this. So if you consider the stator voltage control, it is mainly employed for the particular fan and the particular pumps. So in order to control the speed of fan and pumps. So for fan load torque is proportional to speed square. So now just by taking that, so it is TL is equal to K 1 minus S square. So now we have that TL value and we have that S value, and we can calculate the K value. We can calculate the K value. So now this K is 57.7. Hence TL, we can say it is 57.7 under inside of bracket 1 minus S square. So this is the TL equation, you can say. So at 1200 RPM, if you consider, then S will be 1500 minus 1200 divided by 1500 is it is 0.2. So now at this speed from equation number 1, so this is the equation TL. We can say this as a equation number 1. So at this 1200 speed and at this particular slip, so we can say TL is 57.7 1 minus 0.2 square. So it is around 36.9 Newton meter. So whatever TL is there, so this is at this 1200 speed. So since T is equal to TL, we know T is equal to TL. So T is 36.9. So I can just put here in the equation, in this particular above equation. So now, and I will take 0.2 also, because at 1200 RPM we are calculating. So TL is 36.9, what we got here, and this is already we have, this is the equation for a particular full load torque. This is 3 by 55 V square into 5 divided by 0.2, 2 plus 5 divided by 0.2 square plus 10 square. So this is 0.2 means it is the corresponding slip, that is 1200 RPM corresponding slip. So just by again putting all these, so this B we can calculate. This B we can calculate. This B is 253.2. Now coming to the IR dash. So IR dash will be again V divided by 2 plus 5 by S, that is RS plus IR dash divided by S plus J XS plus XR dash. So it is again IR dash. So now the IM maximum current. So this is V divided by J XM, again 253.2 divided by J 80. So whatever the stator current is there, so in the again equivalent circuit, whatever stator current is there, it is divided into two. One is IR dash, that is rotor current, and another is IM, that is magnetizing component. So now IS is IR dash plus IM. By putting the values, now you can get whatever the IS is there, it is 17.89, 17.8. So in this case, we have calculated the particular IS, then we have calculated the torque, and we have calculated V. This is first point. Then second point, at this particular voltage at 300 volt, so what is asked, again the motor speed, current and torque are asked. So again motor speed, current and torque, again we need to take this particular torque equation first. Again 3 divided 350 of 5, 300 square into 5 divided by S, again 2 plus 5 divided by S square plus 10 square. So again we need to take this particular equation to calculate that S value. So again here in steady state, put this condition T is equal to TL. So again by putting this condition, so we can get the, again therefore from equation number 1 and 2, from equation number 1 and 2, T is equal to TL. This is equation number 1, this is TL is equal to 57.7 1 minus a square, and the equation 2 we have got is again this T, the second condition. So we have this particular T equation just by putting V is equal to 300 square 300. So just by using those two equations we can have this particular equation. So here again we need to calculate the value of S by using this equation. So S is equal to 0.147. So hence torque produced by the motor is T is equal to 57.7 inside of the bracket 1 minus point S square, that is 0.147 square, it is 41.94 Newton meter. So this is the torque corresponding to 300 volts. Now speed will be ns 1 minus s, and it is your speed at corresponding to that particular voltage. Then is again resultant of Im plus I dash. So Im is 300 by J80, it is same. Just we are replacing this 300 here, and plus whatever the I dash is there. So this is the value of I dash, 300 divided by 2 plus 5 divided by 0.147 s plus J10. It is your Is. So hence line current will be 16.88. So this is the example based on the speed control, So hope you understood this. The very important in this is whatever the examples based on the plugging and the particular braking of motor, and the example based on the transient analysis. So thank you.